high. What we have done up to now, sequential circuits that we were examining. Among these, we've got memory elements. We examined memory elements, and we have seen two main problems that we face in memory elements. Solution of these memory elements problems we have seen up to now. Now, finally, we are going to examine commercial memory elements. So up to now we examined theoretically. Now in commercial memory elements, what we see in the data sheets of these memory elements in practice. So we're going to examine these commercial memory elements in this video. Let's move up to open board now. You know we've got to do a bit settling here. Setting, okay. Here we are. Let me clear this area. Easily I can do that. So you see here a JK type memory elements in practice. Two of them put together in one integrated circuit. So you cannot buy only one memory element in practice. You're going to buy an integrated circuit. In this integrated circuit, you're going to have two memory elements at the same time. So that shows this. So two JK memory elements are included in this integrated circuit. So if you look at the data sheet of these memory elements, data sheet we call it. So definition or the function table is like that. So this is not the theoretical case, you see. That's we're going to see the function table. So if you see the function table, there are two additional inputs that we haven't seen in theory. Why do we need that? So you've got to remember the definition relation of JK memory element. I'll just remind you, JK small 0 1 0 0 0 1 1 1 1 0 0 1 0 0 1 0 1 1. So state diagram is going to be something 0 state 1 state, toggling in between. This happens for one input, and for the other inputs it's going to be like that. Most probably like that. Maybe one other change, so something like that. Now when you see that state diagram here, when you see the state table here, you're going to say the small y is 0 or 1. That means your state could be in state A or state B. At the beginning, what state you're going to be in? When I said at the beginning, that means initial state. Initial state. So in circuit theory, that initial state is initial condition. You see, initial condition was VC0 is the initial condition for a capacitor, and IL0 initial condition for an inductor. So these initial conditions, the corresponding initial conditions in a logic circuit is the initial state. So how you're going to set the initial state? Because if you apply an input while your present state is 0, your output observation is going to be different from your initial state in one case. Okay, therefore, you've got to be able to set your initial state to either 0 or to 1. So these additional inputs are used to do this job. That means to set the initial state. So the question is this. In order to set something to 0 or 1, one variable is enough, isn't it? If you've got, let's say, variable p, you might say that when p equal to 0, initial state is 0, when p is equal to 1, initial state is 1. So why I need 2, the reason is here is the initial state. We are going to differentiate initial state from initial state 0 from initial state 1, and also you've got to have another case which is normal working. What I mean by saying normal working, that means when the definition relation works, when definition relation is active, when definition relation is active. So that means now let's examine this table. So the commercial datasheet has got that information. What we've got in this information, the first line tells me, I call this function table. What's the difference between function table and truth table? Is this truth table, if you got 5 variables, you're going to draw here 32 rows. When it is function table, you are reducing the number of rows that you're going to fill in. So it says when the clear and preset inputs, both of them 0, whatever the other inputs are, that means whatever these inputs are, values, whatever it is, your memory element is unstable. That means you cannot estimate what your output is going to be. So never apply. It doesn't mean that if you apply, it burns. So don't consider the unstable case in circuit theory. In here, you cannot say what you're going to observe. For one time you can observe 0, the other time you might observe 1. So undetermined, let's say. So if for different color I'm going to use afterwards. So if you use this one, when the clear is 0, preset is 1, whatever the other inputs are, my output, so this should have been capital Y prime. My output is this, isn't it? So that means initial state 0. That is initial state is 0. So the next, let me change the color. If you apply clear 1 and preset 0, whatever the other inputs are, initial state is 1. So if you look at the last one here, when both of them 1, 1, so now you need the other inputs. According to the other inputs values, you're going to observe this output. Now this is the theoretical definition relation area as it is here. So this table is the same thing here. Still, in this theoretical case, this edge sensitive, when the arrow is upwards, then that means it is positive edge sensitive JK flip-flop, this is. And if you look at this table here, it's the same as here. Just let me show you. When both J and K is equal to 0, that means that row. Your state do not change. That means capital Y. So I'm talking about this. capital Y is equal to small y. That means no change, isn't it? When small y is 0, capital Y is 0. When small y is 1, capital Y is 1. That's this case. So if you look at this second one here, when it is 0, 1, so that means input is 0, 1. Your output is 0, that's this one. When your input is 1, 0, that is the last column here. Your next state is 1. And this last one, when it is 1, 1, the input is 1, 1. That means this. That's toggling it, isn't it? So 0 becomes 1, 1 becomes 0. So this is capital Y is equal small y prime. So this yellow area here is the same as the definition relation that we give in theory. This happened in this mode. That means preset and clear, both of them 1, 1. So I separated this normal working or theoretical working by setting preset and clear 1, 1. And I use the preset and clear to set the initial state to 0 and to 1. So I use those two variables. Okay. Some more information about the commercial products. If there is a small 0 in front of one of these variables, then for example, that clear here. So if you follow this up with red, you see that is the additional input here, clear, and there is a small circle here. The meaning is this memory element clears the present state to 0 when the clear input is 0. Because of that circle, clear equal to 0, that means the other input must be the opposite. That means preset 1, then initial state is 0. So if you look at the other input, that means preset, follow this up, this green one, and this green one has got small circle here. What does this mean? When the preset is equal to 0 because of that circle, that means clear is the opposite, that means a 1, then initial state is equal to 1. So you might ask now, if there is no circle here, that is going to be preset is equal to 1, should be equal to 1 in order to set the present state of the memory element to 1. The preset must be 1, the clear must be 0. That is the opposite of this one. Still your initial state 0, but this is going to be 1, that's going to be 0. That is the difference between having a circle or not having a circle for these variables. That is another practical information that you might need in lab. So let's go a bit further. In here you see the difference between theory and the practice. So this is here theoretical D-type memory element definition relation, but in data sheets you're going to see this type of relation. So this QT plus 1, our capital Y, that means next state. So what it says, when D input is equal to 0, your capital Y next state is 0, whatever your present state is. When D is 1, your next state is 1, whatever your present state is. So this is the same thing, isn't it? When D equal to 0, your next state inside is capital Y. Your next state is 0. If D is equal to 1, so your next state is 1, same thing. But this is in theory. This is in datasheet. So another thing that is related with the clock, if there is no any circle in here, but not this circle is not the same as the preset clear input circles. So if there is no circle here, it is positive edge sensitive or the raising edge sensitive. When there is a small circle here, it is a negative edge sensitive. So it is like that, or the falling edge sensitive. Let's come to the other one. The difference between theory and the practice. Here you are. This is the definitional relation of a JK memory element in theory. That's so theory. And that is in practice or in lab case. What it says, if the input is 0, 0, 0, your next state is the same as present state. That means no change. So this is that column here, isn't it? So your next state is the same as small y. So you can represent this column altogether here with this line only. So when it is 0, 1, so that means JK input 0, 1 is, that means they are opposite to each other. So whatever J says is going to be observed in the next state. So here, J value you're going to observe as capital Y. Here you are. J value explained as 0. So this is this one. When it is 1, 0, that means this case, the last column here. So the output is equal to 1. The output is to 1. And the in between, let's make it green. So for this column, theoretical column, what it says, if your J and K inputs both of them 0, then your next state is the opposite of your present state, isn't it? That means toggling, that is. So this tells me this. If JK inputs are both of them 1, 1, capital Y is equal Y small y prime means this is 0, then this is 1, that is 1, then this is 0. So this is practice, let's say practice or datasheet, you might say. The last one. Here I'm keep this as it is actually. So this is the T-type memory element. So this is in datasheet and this is in the theory. You see the clock, there is no circle in it. That means that's positive edge sensitive. So this tells you how can make a JK flip-flop as a T flip-flop. So you could make a decision whether it is true or not. And this is another practice for you. This here definition relation of D-type memory element, if you consider this brown frame circuit, it behaves as T-type memory elements. So you can analyze the circuit and show that the behavior of that brown framed circuit is the same as this definition relation. So I left it to you. Another two terminology that you might heard in practice is this settling time, that's the settling time, and the holding time. Settling time is the time required to change the state of a memory. So that means if the memory is going to change its state, you've got to stay or wait for that settling time in order to reach to a new state, settling time. Holding time is the time required to keep the input there. So you're going to hold this state there for that time interval before you apply your new input. So that means you've got to allow to do the state change, means settling time, and keep that value there, holding time, and then change your input. So that means settling time, settling plus holding time. You shouldn't change your input. You shouldn't change your state. So that means you shouldn't change your edge, clock edge, in this time interval. So there should be no change in the input and in the clock signal edge in this time interval. This tells me how fast my memory element is. Longer this time, this total time, means slower your memory element. Shorter this time, that means faster your memory element. Faster memory element price is higher than the other types, of course. So the manufacturer tells you that information by using these two terminology. So you've got to know those two terminology as well. And that is the end of this video then.